So for today's notes, we're going to be talking about moment of inertia, which was one of the vocabulary terms that you saw in your knowledge probe for the lab that you did yesterday, or hopefully you did yesterday. If not, then you've got some stuff to work on for that as well. But we're going to compare and contrast inertia and moment of inertia. We're going to define center of mass and apply that to rotation. And we're going to calculate the moment of inertia for various systems. And so we also have these upcoming deadlines, these dates that you see up here, including two things that are due today. One of them being your roller coaster write-up, so hopefully you have that with you to turn in class today. And the other being your bump assignment. That can be turned in online, but this one you should have either already turned it in or be turning it in class. And then, of course, you have your lab that you just did. If you want to get feedback, that's Monday. The due date's next Wednesday, and you have corrections in playlist 1. All right, so center of mass. We'll start with a discussion of what center of mass is, and it is the point of the system that represents the mean distribution of the system's mass. Okay, so the center of mass is the location for a system where an object will naturally rotate about that point. So it's the object's natural axis of rotation. It is possible to calculate the center of mass of an object using the equation that you see there on the screen. However, that is something that is not done until AP Physics 2, so I wouldn't necessarily even ask you to write it down in your notes, but I do want you to be aware that there is a way to calculate it. But in AP Physics 1, we're going to talk about center of mass more conceptually than we will in terms of calculations. Okay, so again, and I know you've seen this term before for center of mass. We've talked about it before, but we're going to be talking about it today with respect to objects that are rotating. All right, so for any object, we can approximate the location of the center of mass based on its mass distribution in an experimental test. Okay, so we're going to do this, or I'm going to do it for you with a meter stick, which I just grabbed from the back of the room. And so if you wanted to find experimentally the center of mass of an object, you can literally just hold it and bring your fingers in closer together, and I'm going to find it when I see that my meter stick starts to rotate. Okay, and so I can already see it's kind of wobbling a little bit as I get closer and closer here. But once I find a point like that, okay, I can see that I have found the center of mass, so I can balance it at this point. I'm only touching it at one point. Where do you guys think the center of mass of my meter stick is? 50 centimeters, yeah. It's got a pretty even mass distribution, and so it's about halfway. Okay, ideally it's exactly halfway, which is where my finger is right now, is at 50 centimeters. Okay, and so you can figure out where the center of mass of an object is by doing just that. If it's an evenly distributed mass, then it'll be at the halfway point. But if you try it with like a spoon or something from a drawer, you're probably not going to be halfway down the length. But you could try it experimentally. When you get rotation, that's when you have found the center of mass. You'll be able to balance it, but you will see it start to rotate about that point. Or yeah, sure, try it with your pencil. That works too. Okay. So again, it's not necessarily at the midpoint if the mass distribution is not equal. Okay. But again, that's how we're going to be looking at it, is conceptually more so than mathematically. So for a normal meter stick, the mass is evenly distributed, so the center of mass is at 50 centimeters. Okay, but what if we were to repeat this test with a large mass on one end? Let's say I attached something to each end of the meter stick, and you can see up on the screen what that might look like. And so I have a large mass on one end and a small mass on the other. Do you think my center of mass will still be at 50 centimeters if I have these masses?
No.
No. Which side is it going to be closer to?
The bigger one.
The bigger one. Okay, and so again, it'd be somewhere over there, depending on what those masses are. Okay, you will see center of mass labeled in diagrams oftentimes with those letters CM. So if you see that, that is what it is referring to. Center of mass is at that point that is labeled here. Okay, and you would expect it to be closer to where the more of the mass is concentrated, so the larger object. Your center of mass should be closer to that. Unless it's evenly distributed, then of course it's halfway. Okay, what if I were to place a pivot point like my finger at the 50 centimeter mark, okay, but with the meter stick that looks like that? What's going to happen if you were to put a pivot point underneath it whenever your mass isn't evenly distributed? Yeah, it's going to rotate. Okay, if you were to place a pivot point at this location shown, when you had a center of mass that's shifted over to the side like this, you are going to get rotation. That large mass is going to go down, that small mass is going to go up, and you're going to have rotation for that meter stick or whatever that object is. Okay, if you do not have support under the center of mass, it will cause your system to rotate. Follow-up question. Okay, which would have a greater angular velocity during this rotation, the big mass or the small mass? They would be the same. Their change in angle would be the same. For a second, don't fall for it. Okay, they would have the same angular velocity. All right, what if I put the pivot point underneath the center of mass instead?
Balance.
Yep, you would be able to balance it. Okay, so if you had the pivot point underneath the center of mass, the system would remain at equilibrium. There would be no rotation. It would be just like this meter stick that I initially balanced on my finger. My center of mass will be shifted into a different position, but you'd still be able to balance it if you were to put support underneath the center of mass of that object. You would have no rotation. Okay, so just as a general rule, if there is no support under the center of mass and it's shifted off to one side, then your system's going to rotate. Okay, so you're going to have rotation if you have a support placed under that object, but it's not under the center of mass, then you're going to have rotation about that center of mass due to that pivot point. All right, so I showed you this slide yesterday, but when we're talking about rotation, we also need to talk about moment of inertia, which is an object's resistance to rotational acceleration. Okay, we talked about inertia previously in the year, which again was the tendency of an object to resist changes in its state of motion. Think of state of motion as velocity. So resistance to change in velocity could be shortened to resistance to acceleration. So an object's inertia is resistance to acceleration. It's a property of the object's mass. When we look at moment of inertia, like we did in the RA yesterday, it is the tendency of an object to resist changes in its angular motion. Thus, it is resistance to angular acceleration, and it is a property of mass and mass distribution, which is two of the things you were testing yesterday in your RA. Okay, so when we talk about moment of inertia, it is the rotational equivalent to inertia that we talked about previously, or to mass, because inertia is a measure of an object's mass. All right, so I have a video clip up here of a demonstration that's going to show you how moment of inertia affects an object's acceleration. And there is a relationship between the two. You should have looked at that relationship yesterday in your RA, but I'm going to show you this video clip and then we will talk about it a little bit more. She does talk about it as well in the video.
So here we have 2 cans of coffee grinds, but I'll tell you, they're not completely identical, except for the fact that they have the same radius and they have the same mass. But they look the same, but internally they're not the same. So what we're going to do is take these 2 cans and roll them down this ramp and see who reaches the bottom first. Whoever reaches the bottom first had less inertia, so less resistance to rotating. So take a look. Which one reached the bottom first? Well, let's go a little bit slower this time and see who actually is moving faster rotationally when it reaches the bottom. Obviously the one in the back. So that means the one in the back has less resistance to rotating or increasing its rotation. So let's take a look. Here's the first jar. This one is filled with rocks. in order to make it so it has the same mass as the other one. But notice they're glued to the outside radius. So there is no actual mass distributed on the inside of the can in that empty space. The other can of coffee grinds, on the other hand, it's a full can of coffee grinds. So all of those coffee grinds are distributed evenly throughout the entire radius. So now that we know what the true difference is between them, let's run this again and see which one really did reach the bottom of the ramp first. The one with the coffee grinds or the ones with the rocks? Notice, it was the one with the coffee grinds. I have the openings to the cans facing the camera. The one closest to us has the rocks in it. The one furthest from us has the solid form of coffee grinds throughout. And it was the one with the coffee grinds that managed to reach the bottom of the ramp first, indicating that it has a lower moment of inertia, which means then it has less resistance to rotating.
So some of you guys actually tested that mass distribution in the RA yesterday. I know not everybody tested that specific property, but that's what this is. It's looking at the mass distribution within that coffee can. They have the exact same total mass, but one of them has the mass evenly distributed, or at least mostly evenly distributed, whereas the other one has it distributed only around the outside. So the groups that tested solidness hopefully already saw this with their test, but if you didn't test that, then that's what you should have seen. Okay, one coffee tin had evenly distributed mass, whereas the other was hollow with all the mass on the outer radius. There was more resistance to acceleration when the mass was on the outside. The one that was evenly distributed had less rotational inertia, less moment of inertia. It was smaller, and that's why it reached the bottom of the ramp first. So you can analyze acceleration to figure out which one has a greater resistance to acceleration and thus a greater moment of inertia. We examined other factors in the lab yesterday as well, so let's go ahead and go over those because we did look at 3 different factors. Your lab group only tested one of them, but we tested the amount of mass, the distribution of the mass, which is basically the object's center of mass, okay, and then the radius of the object, or how far the mass is from the center of mass would be this one, and then the radius, distance of the mass from the axis of rotation. Okay, and so the moment of inertia did depend on all 3 of these things. Changing the mass did affect your moment of inertia. If you tested that, then you already know that. If you didn't test that, your lab tells you to talk to a group that did. Okay, same thing with distribution. Those of you that tested solidness, you did see that there was an effect on the moment of inertia, or really on the acceleration and thus the moment of inertia whenever you changed that distribution. And same thing with radius. Okay, whenever you changed the radius of your object, so long as you kept the distribution the same, you should have seen a change in moment of inertia. Okay, some of those changes were larger than others, some of them were very small changes, but you should have seen a pattern there. Okay, so these are the different factors that affect moment of inertia. Are the amount of mass, the distribution of that mass, and the radius of the object, which is the distance of the mass from the axis of rotation. Okay, so how do we calculate moment of inertia? Well, it depends on what type of object or system we're looking at. You could calculate moment of inertia for a point mass. And a point mass is basically just that. It is mass concentrated at a single point, or you're assuming concentration of mass at a single point for the purposes of that calculation. And the equation for finding moment of inertia for a point mass is I. The letter I is moment of inertia in our calculation. So moment of inertia equals the sum of mass times the radius squared, and that radius is going to represent the distance of that point mass from the axis of rotation. And it's the sum of all of them, because if you have several different point masses, you would have to find it for that system. Okay, but it's the mass of that point mass times its distance from the axis of rotation. So if you have a point mass, that's your equation. However, we didn't have a point mass in our lab yesterday. We had a pulley. and we had rotation about an axis for that object, which was basically looked like a wheel or a disc. Okay, and so there are other calculations for moment of inertia that are based on basic shapes. And so for these types of calculations, you will be given the equation in the question. So the question will say a disk with a moment of inertia of, and it'll have the equation, and then give you the rest of the question. So you'll be able to look these up. You will not have to memorize them. However, I am going to give them to you so that you have them for your notes. Okay, so again, if you don't have a point mass, you're going to have a shape like one of these. A rod could be something like a meter stick. Okay, and you could rotate a rod about an axis of rotation at its center. Okay, and if you were looking at rotation of a rod about its center, the equation for its moment of inertia, its resistance to rotational acceleration, is 1/12 times mass times the length of the rod squared. Okay, so that would be my equation for a rod if I'm rotating it about its center. Okay, but I could also rotate it about its end. Okay, and it's a lot harder to rotate about its end. It has more resistance to acceleration than it does at its center. So if I were to rotate this rod about its end, I would expect its moment of inertia to be greater, and it is 4 times greater. In fact, 1/3 ml squared, where it's the mass of the meter stick or whatever the rod is multiplied by its length squared. Okay, but we're looking at 1/12 versus 1/3. Okay, so that's for a rod. What we did in the RA with the pulley was basically we looked at a disc or a hoop, depending on if you actually filled it in or not. But if you had a disc, okay, rotating about its center, and a disc would be a cylindrical object, kind of like the can of the coffee grounds that was evenly distributed, that would be a disc. Or if you were to like roll a hockey puck or something that had an even mass distribution, it would rotate about its center with a moment of inertia equal to I equals 1/2 mr squared. Okay, so that is the equation for a disc. But if you have a hoop, which is what most of you had yesterday, because most of you were keeping the difference in the radii the same, and it was probably pretty thin on the outside. If you have a hoop, it's going to look like that, like a hula hoop or something. Okay, but a hollow cylinder. And if you have a hoop rotating about its center, your calculation for a moment of inertia is I equals mr squared. Notice this has a greater moment of inertia than the disc, which is what we just saw in the video that I showed you, the clip, is that the disc reached the bottom of the ramp first before the hoop. The one that was filled throughout with coffee grinds reached before the one that had a mass distribution around the outside. And again, if you were testing solidness, you probably saw this yesterday in your results. Okay, we can also look at moment of inertia for a sphere. A solid sphere might be something like a baseball or a bowling ball. A hollow sphere might be something like a tennis ball or a basketball that has empty space inside. Okay, if your solid sphere rotates, sorry, I forgot I had this up here. This is a reminder of the relationship between the disc and the hoop. Your hoop is at the front, there's with the rocks, the disc is at the back. Okay, and you can see that the disc does have greater acceleration and thus less resistance, therefore less moment of inertia. And that's in the equation too. That's what the half is. Okay, but we can look at the same thing with a sphere. And if that solid sphere, like a bowling ball or a baseball or something that is more evenly distributed throughout, were to roll and rotate about its center of mass, it would have a moment of inertia equal to 2/5 mr squared. Again, you do not have to memorize these. They will be given to you, okay, in a calculation. But you might want this chart in case you need it for your math stuff. Okay, whereas a hollow sphere has a moment of inertia of 2/3 mr squared. Notice the same pattern exists between the one that's filled in throughout versus the one that's not. Same thing here. Disc versus hoop. We had a greater moment of inertia for the hoop that had a hollow center. Same thing here. This is a greater moment of inertia for our hollow sphere than it is for our solid sphere. Okay, so you can compare them to each other. But those are the equations that you might need, depending on what shape you have and whatever question you're answering, if you're trying to calculate moment of inertia. Okay, so with that in mind, I have a ramp here with a bunch of objects on it. You can see a disc, a hoop, and 2 spheres, and a block. Okay, it says there are 2 spheres on this ramp, red and green. If their masses and radii are equal, which one of them is hollow and why? What do you think? The green one, because the red one reached the ground first, thus it had greater acceleration, thus it had less resistance to acceleration. So the higher moment of inertia is the one that's slower to the bottom, that's the green one, okay, which should be true for the hollow sphere, if you just compare those 2 equations. Does anybody have a hypothesis as to why the blue cube reaches the bottom first? We have not talked about this, I'm just curious. It doesn't have any rotation. Okay, so we're going to get to it. We're going to talk about energy, and when we talk about that conversion between gravitational potential energy to kinetic energy, well, now we're going to be talking about 2 different types, translational and rotational, but the cube only has one. Okay, so it happens to reach the bottom first. But again, we'll get to that later. All right, guys, for the rest of the class period today, this is what I have for you. I do need your roller coaster data sheets and write-ups turned in today. If you have not yet done so, I need them by 3 p.m. Your bump assignment also due today. That can be turned in online if you don't have it here in class. You can turn that in later when you get home. It's due by 11:59 p.m. And then, of course, your upcoming deadlines for your inertia lab, feedback for that, playlist 1, and then your test corrections and retest. All right, if you have any questions for me today as you're working through any of this stuff, please let me know.